Welcome to the next session, my dear friends. In the previous session, we have discussed about the plain sedimentation tank and the introduction part of sedimentation aided with coagulation. In that, what is the necessity of adding the coagulant and why plain sedimentation is not fit for removing finer suspended material and colloidal and dissolved impurities. All those things we have discussed in the previous session. So in this session, we are going to start the mechanism of coagulant. The mechanism of coagulant. See, what we have discussed in the previous class, what we need two things. One is destabilization of the particle and agglomeration of the particle. These are the two tasks that this coagulant has to fulfill. That this coagulant has to fulfill. So that means, any coagulant when you add, it should be having a mechanism such that at the end of the mechanism, it should settle the particles which are finer. Okay. Now, so there are four mechanisms for a coagulant. That is, first one is ionic layer compression, ionic layer compression, ionic layer compression, and second one is adsorption and charge neutralization. Adsorption and charge neutralization. So second mechanism is adsorption and charge neutralization. Charge neutralization. And third one is sweep coagulation. Sweep coagulation. And fourth one is interparticle bridging. Interparticle bridging. So these are the four mechanisms. These are the four mechanisms that a coagulant will perform. Then, so what is the first mechanism? We will detailedly study what are the different kinds of mechanisms and why these are called as ionic layer compression, adsorption, sweep coagulation, interparticle bridging. All those things we will learn. Okay. So first one is ionic layer compression. Generally, so the finer suspended material, generally they carry a negative charge because of the wear and tear or the friction of the fluid during its movement. Because of the friction, they carry a negatively charged charge on their surfaces. Now, bringing all these negative charged particles together, ionic layer compression. So, the positively charged ions present in water will surround the negatively charged colloidal particles, and the colloidal particles are sufficiently compressed. Okay, because of this van der Waals forces, the colloidal particles tend to attract. So that means, so whenever I told you in the previous session the Stern layer. So Stern layer is because of the positively charged particles. So that positively charged particles offered by the water. Okay. So offered by the water. So because of which all these negatively charged ionic layer means all the negatively charged particles come and form like a layer on which these positively charged particles will come and stick. That kind of layer is called ionic layer compression, bringing all the negatively charged particles together by some positively charged particle. Maybe before addition of coagulant, that role is played by the water. So after addition of the coagulant will take care of it. Okay. So that means this is nothing but the concept is ionic layer compression, bringing the negatively charged particles together by some positively charged particle. That is nothing but ionic layer compression. Okay. So the positively charged ions, the positively charged ions, the positively charged ions, the positively charged ions present in water surround the negatively charged particles and form a layer which is sufficiently compressed, So either it may be positively charged particle, maybe from water, or any kind of ions present in the water, anything. That is nothing but ionic layer compression. So once the ionic layer compression has occurred, now the second thing is adsorption and charge neutralization. Adsorption and charge neutralization. See, the term itself says adsorption. That means this positively charged particle will come to the ionic compression layer. Okay, ionic layer after compression, then they will adsorb on the negatively charged particle and they neutralizes the negatively charged particle. That is nothing but adsorption and charge neutralization. The coagulant, generally it is a multivalent metallic cation. Okay, we use coagulant. The coagulant is a multivalent metallic cation. The coagulant is a multivalent metallic cation which is having a tendency to adsorb, on negatively charged, the negatively charged particles. And neutralize the charge, okay, so that the attraction between them will increase. So earlier they are having a repulsive force. Now because of the charge neutralization, at least that repulsive force will go away, attraction will improve. Okay, after this charge neutralization, the attraction between the particles will improve. Okay, when filter alum or Al2SO4 thrice 18H2O reacts in water, okay, it reacts in water. That means we use multivalent metallic cations for this work. For this adsorption and charge neutralization, we use multivalent metallic cations. One of the examples of multivalent metallic cations is alum. Okay, so example is alum or simply filter alum or we can call it as filter alum. Okay, so we can call it as filter alum also, which is having a chemical formula of Al2SO4 thrice 18H2O. Okay, once it dissociates in water, so once we add this alum to water, then it will form aqua metallic cations. That means they form metallic cations in the presence of water. That is called aqua metallic cations. Such as AlOH2 plus, AlOH twice, AlOH thrice, which is a precipitate, AlOH thrice is a precipitate, and H plus and Al7OH17 4 plus Al17 OH7 Al7OH17 4 plus Al7OH17 4 plus and H plus ion and H plus ion. These are the different molecules will form when the coagulant like filter alum added to water, when you add it to water. Okay, now here these are all multivalent metallic cations. These are all charged with positive, so more positive charge is there which will help us to neutralize the negatively charged particles. So we need more charge. Okay, that is why we use aluminum, iron like kind of coagulants. Okay, they are having more charge. So this is nothing but adsorption and charge neutralization. So adsorption happens when positively charged particle reaches and adsorbs with the negatively charged particle. That thing will happen when you add alum to the water by forming these kind of aquametallic cations. Okay, these kind of aquametallic cations. So next is sweep coagulation. This is nothing but adsorption and charge neutralization. Ionic layer compression is over. Next mechanism is sweep coagulation. Sweep coagulation. So sweep coagulation is nothing but when these particles charge neutralization is over. Once charge neutralization is over, then the particle will start attracting. Okay, then particle will start attracting. Sweep coagulation. Sweep coagulation. So here after adding coagulant, the flock is forming. Here in this previous one I have shown a term called flock, AlOH thrice. So this flock is a amorphous gelatinous precipitate. Okay, after addition of coagulant, it forms flock. Al, for example, for filter alum, I am talking only for filter alum because filter alum we use for water supply. That is why I am taking filter alum as example. Okay, if it is another type of coagulant, there also flock will form. That is, if you are taking iron, then FeOH thrice is the flock. If you are taking lime, CaOH twice is the flock. So there are different kinds of flocks, but in water supply we use filter alum as a coagulant. That is why I am taking filter alum as example every time. Here the flock which is formed by the filter alum is AlOH thrice. So this flock, so it forms flock which is amorphous, it is shapeless, gelatinous precipitate. This is amorphous gelatinous precipitate. So it is having a gelatinous, that means attractive nature. Okay, it is having an attractive nature which attracts the neutralized colloidal particles. Okay, which attracts the neutralized colloidal particles. So So because of this attraction, what happens? They will come together and forms a flock. That means if it is having AlOH thrice here, so this AlOH thrice will attract all the finer particles. So this is called flock. And AlOH thrice will form microflocks. So this is AlOH thrice, this is AlOH thrice, this is AlOH thrice. These are called microflocks. These are called microflocks. See, sometimes microflocks are also not sufficient for the particle to settle. Okay, for sometimes microflocks are not sufficient, they will not have sufficient gravity force, that is sufficient gravity force to let them settle. So sometimes these are also not enough for settling. We need some extra. And the mechanism what we are discussing now is sweep coagulation. That means why we are calling it as a sweep coagulation, as I told you, these are all microflocks. Still they will be having kind of a Brownian motion. Their size will not allow them to settle like a discrete settling. So they will be having some kind of Brownian motion. So this is called sweep. So whatever the particle during its movement like a Brownian motion, they will come and stick to the flock. They will come and stick to the flock. That is why we call this as sweep coagulation. Sweep coagulation. Okay. Next is interparticle bridging. Interparticle bridging. So this is what the term, if you read the term properly everywhere, the term indicates the definition. Interparticle bridging means what? Interparticle. So particle, it is bridged by some person who can hold these two microflocks. So the microflocks are held by heavy metallic cations. Okay, microflocks come together. Microflocks come together and stick to heavy metallic cations. Heavy metallic cations to form macroflocks. If you look at the aquametallic cations that are formed when the alum is added, in that one heavy metallic cation is formed, that is Al7OH17 4 plus. Al7OH17 4 plus. This is a heavy metallic cation. This is a heavy molecule which is formed during the addition of alum to water. So this will hold the microflocks. So on the one side it will hold some microflocks on the surface, so everywhere. So now what is happening? So now these microflocks which are coming together and stick to this heavy molecule, that is Al7OH17 4 plus, and now it has become macroflock. Okay, it has become macroflock. So when the size is increased, then it is easy to settle these particles. It is very easy for us to settle down these particles. So this is interparticle bridging. These are all the mechanisms when a coagulant is added to water. See, one thing you need to note down here is, it is not necessary to have all the mechanisms at a time. So sometimes in some kind of it varies from water, it varies from the alkalinity, it varies from the size of the particles present there and the nature of the particles present there. So sometimes with sweep coagulation the total thing will happen. Sometimes we may need interparticle bridging also. Sometimes with charge neutralization itself the particles will settle down. So we don't need all the mechanisms to happen, but the main motto here is that should be destabilized, that should be agglomerated. These two should be happened. So if one mechanism If with one mechanism if it is happening, then with one mechanism only the settlement will occur. With one mechanism it is not happening, then 2 or 3 mechanisms may be needed. That we will understand at the end of the session. We will understand what kind of material will have what kind of mechanisms in it. That we will understand in the coming concepts we will learn. So what I want to tell you here is, all the mechanisms may not be needed to happen at a time. It varies from water, raw water having colloidal particles in it, nature of it and properties of it. Many things will affect the mechanisms. Okay, so these are the mechanisms of coagulation. And now what are the different kinds of coagulants we use in our environmental engineering or water treatment? Maybe it may be a wastewater, it may be fresh water. So what are the different kinds of coagulants we use? Let us see. Common coagulants. So the common coagulants which we use: alum, already we have discussed. Alum, Al2SO4 thrice 18H2O. This is alum. Next is copperas. Copperas, FeSO4 7H2O, FeSO4 7H2O, and third one is chlorinated copperas, chlorinated copperas, FeSO4 is here, it is same copperas but we add chlorine. We will see the reactions later, because it is not simply one formula, it is having a multiple reactions that we will learn afterwards during the explanation of these chlorinated copperates. Next is sodium aluminate. Sodium aluminate. Sodium aluminate. Na2Al2O4. Na2Al2O4 and lime. So these are the different kinds of coagulants we are having, but majorly for water supply we use alum. For water supply we use alum. So we will establish a comparison between the aluminum flock and iron flock. There are these two are generally we use this for these two for wastewaters. Okay, we use this for wastewater. So we will establish a comparison between the iron flock versus aluminum flock. We will understand why we are not using iron flock for water supply, why we are using only iron flock for wastewater. That we will discuss it in clear way once we go into the concepts. Okay, first one we are going to discuss is alum. Here in water supply it is very important for the examination. Alum and its reactions when we add it to water, all those things are very important. Okay, so alum, Al2SO4 thrice 18H2O plus C. We seen the aquametallic cations which are formed when we add this alum to water. What are the aquametallic cations that has formed? Al OH 2 plus Al OH twice 1 plus Al OH thrice Al 7 OH 17 4 plus. So these are all the metallic cations which are forming. So this OH, it is taking from H2O only. Now all these, when all the OHs are taken by this alum, and it is releasing what? H plus ion. It is releasing outward H plus ion. That means alum to work. So listen carefully. When an alum, if it needs to work, it has to have a friend, that is OH. Without OH, alum cannot work. Without OH, alum cannot work. So OH means what? Alkalinity. OH means what? Alkalinity. So this OH, this much OH should be present in the water. That means if OH is present, that means alum works in a better way. If OH is absent, see, two things are happening here. One thing is alum is taking OH, releasing H plus. This H plus increasing the acidity of the water once the alum is added. Okay, so it will take the OH minus present in the water and releases H plus. Now this H plus also finds OH minus present in the water. That means again this H plus, if it is having more affinity, then again it will take the OH back. So that means when you create acidic environment in the alum cannot work effectively, because these two wants OH. Al also want OH, H plus also want OH. So they will fight each other. They cannot work together. They are enemies. They both want only one compound, that is OH minus. That means in order to alum work effectively, H plus should not present in the water. That means you need to create a basic or alkaline environment. In alkaline environment, H plus will not present. Sufficient amount of OH minus ions will present. That is nothing but alkaline environment. That is why we need an alkaline environment here for alum to work effectively. So we will create the alkaline environment either through the water. Some alkalinity may be present in water. If alkalinity which is present in water is not sufficient, then we need to give alkalinity to the water externally in order to make the alum effective. Are you getting my point? So everywhere alum will work only if it is having OH minus ion with it. So if OH minus ion is not present sufficiently in the water, then we need to give it externally. That is called alkalinity. So alum plus alkalinity only forms the flock. Okay, only forms the flock. So alkalinity we generally give in different ways. So I am taking here in the form of calcium bicarbonate. I am taking it here in the form of calcium bicarbonate. Okay, CaHCO3 twice. So if you are taking it in the form of a calcium bicarbonate, then it forms 3CaSO4 plus AlOH thrice. This is flock. This is called flock. 2AlOH thrice, and CO2 plus 18H2O 6 CO2 plus 18H2O. So this is the reaction after addition of alum in the presence of alkalinity. That is the reaction will form. What are the products and all we will think of later. First, the products will form when you add this to the alum. So first of all, what is your basic study is for some amount of alum, how much amount of alkalinity is needed. That you need to know as an engineer. we need to know for effective work of alum needs alkalinity. So what is the dosage of alum is needed, that we need to know, and for that dosage of alum how much alkalinity is needed, that we need to know, and again whether that alkalinity is present in water or not, that we need to understand. If it is not present in sufficient quantum, then how much we need to add externally. These things are needed for an engineer. So that is why we are going to study those concepts. What are the products and all, we will think of it later. Products will form when you give sufficient reactants. So let us focus on the sufficiency of the reactants first. Okay. Now here, to understand this, so we need to first find the requirement of alkalinity for unit, for single unit of alum, how much alkalinity is required. For that we need to know what is the molecular weight of alkalinity, for what is the molecular weight of alum. What is the molecular weight of alum? So the molecular weight of alum, so this is 666. So if you calculate it also, you will get the same value. Al2SO4 thrice 18 H2O, its molecular weight will be 666. And here calcium 40, 61 into 2, 40 plus 61 into 2, that is how much? It is 186, I think so, it will come around. So 42, 122 plus, that is 162. Its molecular weight is 162 into 3, 486. So it is 486. So here 666 units of alum needs 486 units of alkalinity as bicarbonate. Okay. So 1 unit of alum. So if 666 units of alum needs 486 units of alkalinity as CaHCO3 twice. Then 1 unit of alum needs 486 by 666 units of alkalinity as CaHCO3 twice. Now here, if x mg per liter, so the alum dosage now it is fixed as x mg per liter. If x mg per liter, for x mg per liter of alum dosage needs 486 by 666 into x mg per liter of alkalinity as CaHCO3 twice. So this is very important. For x mg per liter of alum dosage needs 486 by 666 into x mg per liter of alkalinity as CaHCO3 twice. This CaHCO3 twice can be also created by different ways. Okay, this CaHCO3 twice, when it is heated or when it is added with some water. So there are many reactions that are present with CaHCO3 twice. Let us see all the reactions first. See here, this is CaHCO3 twice when heated it will become 3CaCO3 plus H2O, 3H2O plus 3CO2, 3CO2 plus 3H2O. Okay, that means either the reverse thing also. When you add CaCO3 plus CO2 plus H2O, then it will form CaHCO3 twice. Okay, then it forms CaHCO3 twice, and again this CaCO3 upon heating, this is called calcination. Upon heating it forms CaO and CO2. This 3CaCO3, it forms 3CaO plus 3CO2 plus CO2. Okay, this is called calcination. This is called calcination. And next is this CaO, if I added with water, this is CaO, if we add water to it, this is called slaking of lime. Slaking of lime. So which is called it forms hydrated lime. This is called hydrated lime. It's called hydrated lime. Again, this hydrated lime is added with CO2. Again, this hydrated lime, it is added with CO2, it forms CaCO3. It forms CaCO3 plus H2O plus H2O. So either this CaHCO3 twice can be brought from CaCO3, and CaCO3 can be brought from CaO. That means, so you can procure the alkalinity. So alkalinity can be alkalinity can be provided by CaO, that is quicklime, CaO, that is quicklime. So this is called quicklime. Or by CaCO3, calcium carbonate, or by CaHCO3 twice. So in any means you can procure the alkalinity, by any means. So in examination they will ask you, if you are procuring in the form of quicklime, how much is needed? If you are procuring in the form of calcium carbonate, then how much is needed? Then how much alkalinity is needed in the form of calcium bicarbonate? So these kind of questions. So they may ask alkalinity in terms of quicklime, in terms of CaCO3, in terms of calcium bicarbonate. All the relations are needed for us. All the relations are needed for us. Now we have derived one relation, that is 1 x mg per liter of alum needs 486 by 666 into x mg per liter of alkalinity as CaHCO3 twice. Now in the same manner, what is the need of alkalinity in terms of CaCO3? What is the need of alkalinity in terms of CaO? That we are going to learn. Okay, that we are going to learn. One thing we need here is, this thing is needed for 666 units of alum needs 486 units of alkalinity as CaHCO3 twice. In turn, this 486 needs 300. In turn, 486 needs 300 units of CO3. That means if you relate 666 needs 486, 486 needs 300. That means 666 units of alum needs 300 units of alkalinity as CaCO3. 300 units of alkalinity as CaCO3. Similarly, this 300 needs 3 into 40 plus 16, 56, that is 168. Okay, 3 into 168, this is 168. In turn, 666 needs 486, 486 needs 300, this 300 needs 168. That means again 666 units of alum needs 168 units of alkalinity as CaO. I repeat it again, please listen carefully. I will write it and I will repeat it again. See here, so alum Al2SO4 thrice plus 3 CaHCO3 twice gives rise to CaSO4, 3 CaSO4 plus 2 AlOH thrice plus 6 CO2 plus 18 H2O. Now this 3 CaHCO3 gives rise to 3 CaCO3, 3 CaCO3 plus 3 CO2, 3 CO2 plus 6 H2O plus 3 H2O, 3 H2O. Again this 3 CaCO3, again this 3 CaCO3, 3 CaO plus 3 CO2. So this is what is the reaction, right? This is what is the reaction. So 666 units of alum needs 486 units of alkalinity as CaHCO3 twice. That is equal to this needs, so this alkalinity needs 300 units of alkalinity as CaCO3. So this 486 needs 300. This is 486. This needs 300. This 300 needs 168. This 300 needs 168. Okay. This 300 needs 168. So this 300 needs 168 units of alkalinity as CaO. So take it in reverse manner. So 3 CaO plus 3 CO2 is 3 CaCO3. 3 CaCO3 plus 3 CO2 plus 3 H2O is 3 CaHCO3 twice. So that means, so for creating this from quicklime, then this is the reaction. Quicklime, we need to add 3 CO2, then it will form 3 CaCO3. For 3 CaCO3, if you add 3 CO2, 3 H2O, then it forms 3 CaHCO3 twice. So this is the relationship. This is the relationship. Now we can write the equations of the requirement of alkalinity in any terms, okay, in any terms. That how to write those formulas and all, we will discuss it in the next session. Thank you so much.